Assalamualaikum. My name is Muhammad Shazim. Now I will explain about single line diagram. So this single line diagram provides a structure technical overview of the electrical distribution system, starting from the main incoming power supply protected by high capacity molded case circuit breaker, which is MCCB, and distributing through a center copper bus bar. The layout utilizes a series of miniature circuit breaker, which is NCB, and residual current device, RCD, to branch into specific final circuit, such as 10 ampere of line for lightning and 20 amp or 32 amp line for power outlet. Each to ensuring that each zone is independently protected against overcurrent and earth leakage fault. By considering the complete three-phase or single-phase wiring into a simplified functional map, the drawing clearly communicates the system load requirement, protective coordination, and safety compliance for the entire installation. For the single line diagram, it uses three-phase electrical incoming, which is red, yellow, blue, and neutral. Electric circuit described in the single line diagram is structured as a comprehensive power distribution hierarchy, engineered to transition safely from a high capacity main source to specialized final branch circuit. At the start of the change, the system is fed by a primary incoming supply, typically utilizing heavy-duty 16 mm or 25 mm copper cabling, which enter a main molded case circuit breaker MCCB designed to protect the entire installation from catastrophic thermal or magnetic fault. From this control point, the electricity is energized across a common copper bus bar, which acts as a distribution spine for various sub-circuits. These sub-circuits are strategically segmented to ensure that high demand load do not interfere with sensitive one. For instance, lighting networks are wired with 1.5 mm cables and 10 amp miniature circuit breaker, while general purpose power socket use thick 2.5 mm or 4.0 mm wiring pair with 20 amp or 32 amp breaker to accommodate appliances with higher current draw. Furthermore, the drawing includes dedicated radial circuit for heavy-duty equipment like air conditioner and water heater, ensuring these devices have a direct uninterrupted path to the board, while a protective residual current device monitor the entire loop for earth leakage to prevent electric shock. This is systematic approach, supported by a continuous grounding network, ensure the electrical infrastructure is not only balanced across phases but also high resilient, allowing specific zones to be isolated for maintenance without.
So looking at this load calculation, the total connected load for the whole house is 62.5 kilowatt. However, since we don't turn on everything at once, our actual maximum demand comes down to 55.26 kilowatt after applying the diversity factor. We have balanced the paces, but the red paces is carrying the most weight because of the heavy-duty stuff like the water pumps. The main takeaway here is that our system is only running at about 65% capacity. This means the design is very safe, not overloaded, and we still have a solid 35% spare capacity for any future upgrade for additional appliances. For the system performance analysis, first is space balancing and EV readiness. Beyond this figure, we intentionally keep the blue base load lower to dedicate capacity for future EV chargers. This ensures the spaces remain balanced, preventing high natural current and energy inefficiency. Second is system reliability and operational safety. The second point is regulating our 35% spare capacity. By not running the system at its maximum limit, we reduce heat stress on cable and protective device. This improves energy efficiency and significantly extend the overall lifespan of the electrical installation.
For this part, cable sizing, the objective to select the most economical cable that ensures safety against the overheating and maintains efficient voltage delivery. Next, to delivery, to verify that all feeders and subcircuit comply with safety standards. Next, for the observation, this table covers the heavy lifting from the transformers to main switchboard (MSB) and down to the distribution board (DB). So for this table, firstly we have feeder path. IB is a design current, the actual the load will draw, and this one is calculated from load calculation. Next we have IN, MCB, nominal rating, the rating of circuit breaker protecting the cable, and this one is from standard sizes for breaker. Millivolt per ampere per meter. This one is from cable manufacturer catalog specific to the cable size. And for voltage drop, for the calculation we need to from millivolt times IN times length and divide by 1000, we got the VD. And next for VD percent, base for feeder path we need to divide by 400. So the calculation and formulas from V voltage drop divide by V supply, which is 400, and times 100. So we get the result. And for cumulative, we need to calculate from based on voltage percent, and then from the first voltage percent we got 0.036. Next we need to calculate from 0.36 plus 0.139 from the voltage drop. So the calculation maintain and get the result. Next for ITAB catalog A, the base current capacity, also from cable manufacturer catalog or standard tablet. Next CA 35 Celsius, ambient temperature correction faster, base also sourced from electrical standards. Since Malaysia is hot, we reduce the allowed current if the air below 30 Celsius. CG grouping factor sourced from electrical standard too. So for Isaac effectiveness or the real world capacity, we need to calculate ITAB times CA times CG, and then we get the result and check from Isaac to IN. The cable real capacity Isaac must be higher than the breaker, so the breaker trips before the cable melts. So for final sub-circuit item is same from the feeder path, but for this one VD supply we need to divide by 230, not 400.
Assalamualaikum, my name is Aiman Iqbal Fazi. My metric number is P1124100187, and I will be talking about the short circuit and protection system. Firstly, we will be talking about the PSC. The PSC can be calculated, but for this table, I'll take it from the table that is given from the cable sizing. For the transformer and MSB, we have a same PSC of 33 kA. We'll be using the MCCB rating of 36 kA. And for the ground floor and first floor DB, we'll be using the PSC of 4.44 kA and 1.2 kA, which is lower. So we'll be using the MCB rating of 63 MPMCB and the 6 kA breaking point. For the lower table, we have a curve type and its load. For using the ideal curve type, we will be calculating using the earth fault load impedance, which is Z measured is lower than the Z calculated. For example, the light, we using the lighting. Z measured is 1.93 and Z calculated is 4.6. That is the ideal curve type for the load. But for the other loads, we are using the extra curve type, which is, for example, the water pump. We're using the type D because it has a high intensity current rush. And for the aircon, we're using the type C because it has a high motor starting current. And for the power socket and kitchen appliances, we can use the type B for the curve type B, but we're using the type C because we will have a multiple loads, a mixed loads of multiple equipments that we'll be using, and there is no current limit that we can calculate. So we're using a higher to prevent a nuisance trip and braking. For the EV charger, we are using the type C, higher curve type because it is a power electronics. We also will be using a high electric current. For the earthing and safety, we will be talking about the earthing first. So, the earthing that has been selected by us is the Terra earthing system, or will be called a TT earthing. Why? That is because the TMB supply does not guarantee earth continuity. It is safer for residential buildings, and it is independent consumer. It has an independent consumer earth electrode. Also, it is mandatory by Suruhanjaya Tenaga ST for landed houses. There is plenty of reasons to be using the TT. There is other earthing systems, but we choose this one because it is the most suitable for our house. Lastly, I'll be talking about the PE conductor size. For a transformer, we will be using the 75 square millimeters. That is because when the size is bigger than 35, when S is bigger than 35, we will be using the formula of S over 2, which will be divided. So 100 for the transformer, we have 150 load. So 150 divided by 2, we will get a 75. That is the size of the PE conductor size. For the MSB, the load is 35, which is the S. When the S is equal or less than 35, we will be using the 16 square millimeters. Both of these are the for the transformer, that is calculation, but for the MSB, which is the 35, that is a specified sizing that has been set. For the lighting, power socket, and for the other loads, we'll be using exactly the same size as the S size. That is because when the S size is lower or equal to 16 square millimeters, we will be using their own size.
Looking for this BOM, the first thing we emphasized was component quality. We didn't just pick random part, instead all protective device like the SPD and RCCB must compile with IEC standard. This is important because we need to protect the expensive electronic in this bungalow from lighting, triggers, or short circuit. So safety was the number one priority in selecting this material. Okay, next, we specify different size based on the load. For example, for the EV charger and large eco unit, we allocate square millimeter cables. Although these are more expensive, they are essential to prevent overheating during long hours of EV charging. We're designing the system for the long haul, not just a couple of years. This is why the total project cost comes to Rm 40,158.1. This figure covers high quality material and include a 10% contingency cost, making the budget very realistic. While it may seem premium, the homeowner is actually investing in a system that is safe, stable, and most importantly, future-proof. One last point, we make sure to include testing and commissioning element. Basically, after everything installed, we must conduct mandatory tests like insulation and earth resistant tests. It is not just to comply with Suruhanjaya requirement, but to prove that the calculation in our report actually work and 100% safe once we turn the power on.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Rifai bin Muhammad Ibrahim. My matric number is B1124101885. Today, I will briefly explain the power distribution layout for this building, which consists of the ground floor and the first floor. Overall, the power distribution system is designed to ensure that electrical supply is delivered in a safe, efficient, and organized manner to all areas of the building. Electrical power is distributed from the main distribution board and then divided into several circuits to serve lighting point, power socket, and electrical equipment according to their load requirement. Starting with the ground floor, the power distribution mainly support common and functional areas where electrical demand is relatively higher. Separate circuits are provided for lighting and power socket to prevent overloading and to improve safety. This design also allows easier troubleshooting and maintenance if any fault occur. Moving on to the first floor, the power distribution is arranged based on room function and usage need. Each circuit is carefully planned to provide a stable and reliable power supply. The layout ensures balanced load distribution, which help reduce voltage drop and minimize the risk of electrical failure. In conclusion, this power distribution layout demonstrates a well-planned electrical system where both floors receive adequate and balanced power supply. The design follows standard wiring practice, enhance safety, and allow flexibility for future expansion or additional electrical load. Thank you for your concern and attention. Assalamualaikum.
In summary, this electrical system has been comprehensively designed to balance technical performance with long-term safety. By integrating precise load calculation, a strategic 35% capacity safety margin, and high-quality component, the system ensures maximum reliability and compliance with MSIEC 60364 standards. This design not only meets current household need, but it also fully optimized for future technological integration, specifically EV charging, making it truly robust and future-proof infrastructure.